Right. Good afternoon, everybody, and thank you for taking the time to join us today for this presentation on industrial 3D printing of metals, ceramics, and polymers. So my name is Michael Petch. I'm the editor-in-chief of 3D Printing Industry, and I'll be your host and moderator today. Now, today's format will be 3 short presentations. Each presentation will be followed with a Q&A. So please do use the Q&A tab on the right-hand side of your screen to ask questions. And we can ask questions of each of the 3 panelists. In that Q&A box as well, you're also able to upvote the questions you'd like to see answered. So please do make use of that ability there. Should we not get around to answering all of your questions during the presentation part of our event, do not fear, we will be following this up with a more informal networking style event, and after this main part of the presentation finishes, everyone will be moved to those networking areas. Now this is, in these networking areas, you'll be able to ask questions directly from the company representatives who are here today, and hopefully get any answers you're looking for. We are recording the event as well, so if you do need to leave, there will be a replay available for you. So on with the show, which today is the industrial 3D printing of metals, ceramics, and polymers. Now, in recent years, industrial 3D printing has rapidly evolved to a complementary production technique alongside traditional manufacturing, covering applications from small series to large-scale production. Among these technologies, a new generation of lithography-based additive manufacturing processes have emerged, and the ability of 3D printing metallic, ceramic, and polymer objects in industrial-grade quality brings professional additive manufacturing to your production floor. Today, we have 3 Austrian manufacturers, Incus, Lithoz, and Cubicure, and they will showcase how lithographic 3D printing technology enables the production of strong, highly precise, and functional metal, ceramic, and polymer components in various industrial fields. And they will introduce the specific strengths and characteristics of the technologies involved and examine their suitability for industrial production. So I would like to welcome our panel today. So we have from Incus, Dr. Gerald Mitteramskogler, who is the CEO of Incus. We also have David Schuller, who is the business development, head of business development at Lithoz. And we have Dr. Robert Gmeiner, who is CEO and CTO at Cubicure. Hello, everybody. Can you hear me?
Yes.
Hello, Michael. Yes.
Hello, Michael. Also, hello from Incus.
Good afternoon and welcome, everybody. Thank you for taking the time to join today. So remember, there will be 3 presentations. There will be opportunity to ask questions after each presentation. So make sure you use the Q&A function there. First off this afternoon, Incus will be giving a presentation. So Incus, if you're not already aware, is an Austrian engineering company founded in 2019, I believe, and a system provider for the unique lithography-based metal manufacturing technology, which is a novel 3D printing process developed that offers an economic method for prototyping and using from small to mid-scale production of components in metal injection molding quality. Gerald, CEO, you have 11 years experience, that's correct, in additive manufacturing, and you'll be sort of telling us about the challenges of metal manufacturing and how you founded Incus to introduce innovative 3D printing technology for producing complex parts. So Gerald, I'd like to invite you, please take it away.
An introduction. I hope you can all see my screen at the moment, and hopefully in a full screen. So today I want to show you our process we developed, lithography-based metal manufacturing. I just jump into the topic. Michael gave a nice introduction of myself. My name is Gerald Mitteramskogler. I'm the CEO of Incus, and before that I was a material developer at Lithoz, our mother company, and then also head of the metal division. And in September 2019, we decided to spin out the metal additive manufacturing world into Incus, the new company. So basically, who is Incus? Yeah, we are a system provider for the metal additive manufacturing based on lithography. So we actually sell the printers and the materials, but we also do innovation studies with our customers. So we are not really a part producer. This is the business of our customers. As I mentioned before, we are the spin out of Lithoz, and we're also a proud member of the AM Ventures portfolio. So how quickly our production chain. So basically we start off with the 3D imaging. So you have to have a 3D model. Then you go into the 3D printing process. So layer by layer, we build up a so-called green part. I will explain later on what a green part is. Then you need to do a decaking or a depowdering step to get to the final green part, to the printed part. Then in any sinter-based or indirect additive manufacturing technology, you need a debinding and sintering step to get to the final metallic properties. And yeah, we at Incus, we are the experts really to get you to the printed green part. And we have strategic partners or our customers who are experts in debinding and sintering to really in these essential steps to generate the metallic properties of the material. So let's jump into the lithography-based metal manufacturing. How does it work? So in general, it's a wet polymerization additive manufacturing method. It's a top-down machine design where we recoat a new layer of material with this heated blade. So we lay off a new layer of liquid material and then solidify it with the projector unit or the DLP engine. And basically with light and photopolymerization, we build up this so-called green part layer by layer. The special thing is, or the secret sauce for us is the photoreactive butter-like feedstock. At room temperature, our feedstock, the raw material is solid, and at coating temperature around 30-40 degrees Celsius, it turns liquid. So we always coat a liquid layer of material on a solid surface, and that allows us, together with the high quality DLP or projector unit, to create parts in the highest possible surface aesthetics and accuracy for metal additive manufacturing. So what's also indicated in this scheme on the right side is that we don't need supporting structures to connect the parts to the building platform, and we can print overhang structures, yeah, also without any connection to the building platform. I have a short video, I hope it runs smoothly for everybody, showing the printing process. So here is the recoating of a new layer of material. So in this case, we print stainless steel with a layer thickness of 20 microns. And after the coating process, you see the polymerization with blue light. And yeah, the printing process doesn't get more exciting than that. This is how it looks like layer by layer. And on the right side is the set stage, so the printing stage, which moves down layer by layer. And on the left side, you see the material piston. So as the set stage moves down, the material piston adds material to the printing process. So we never run out of printing material. So as you can imagine, after the 3D printing procedure, the green parts are all submerged in this block of material. So the second thing I mentioned was the decaking process, and this looks like the follows. That's my favorite processing step in this whole production chain. It's the melting of the feedstock block, and you see here that the material melts, and the green parts, which are solidified by the blue light, can be extracted. So I'll let it run once more so you see what's actually happening. So at around 30 or 40 degrees Celsius, the butter-like feedstock melts, and only the printed green parts stay behind. So in the back, you see the St. Stephen's Cathedral in Vienna. And here you see that the parts actually fall down on each other. So they have been printed with about 1 millimeter apart in the set direction. And this is kind of also a unique process in this whole, in metal 3D printing approach. So here you just see a few printed green parts. Once again, in this example, you see that absolutely no support structures are needed to print the green part. Also, if you have complex structures like this, no support structures are required. But you can not only print smaller structures, also those are one of the larger parts we printed. Those are drilling heads with some complex internal cooling channels. You see the combination of this high homogeneous coating process together with lithography yields this high quality surface aesthetics you see on the green parts. But the green parts are only the first part of the story. You need to do a thermal post-processing or the debinding and sintering step. And this is also a very, very important process step, of course, because here you generate the final metallic properties. So you see the direct comparison of the printed green part on the top, and on the bottom is the sinter part, also in this case with stainless steel. And you have a shrinkage of roughly 20% in every direction. So you need to scale up the model before you put it in the printer, and by this you can create the final geometry. So this is not something we invented. This is also commercially done, or was done before, in the metal injection molding technology. So here controlling the shrinkage is already more or less under control. So here I want to show you a few final applications we did with our printer. So first, before that, I've shown you the drill heads. Another really interesting applications for us, electronics or small connectivity components. So in this case, you see on the right side, it's a part of that running too fast. Sorry for that. You see the component of a mobile phone. Here the SIM card would be inserted in the mobile phone device, and this part and all of the parts you've seen before are done without any surface processing. So the surface is as sintered, and I really see this, find it interesting, the comparison of the texture of the glove compared to the texture of the sinter part itself. So here we have a development partner, Element 22 from Northern Germany, who we printed this part with. Another really interesting example, one of my favorites as well, is the medical or dental field. On the right side, you see dental brackets. Sorry again, moving a little bit too fast. That they are made with our partner Micromim in Japan. So Micromim, as implied in the name, they're focusing on really smaller, delicate structures. And here it's important that the surface aesthetics or the material quality is the same in any printing direction, because as you see here, no support structures are needed, and the surface quality in the bridge in the middle is all over the surface. It's the same. So here not much post-processing is needed to get to the final part. Another application is R&D, and here we have a strong debinding and sintering partner, and also in Germany, the company MedShape, and they're doing the designing, the debinding and sintering for us. So here on the right side, you see an internal application, which is a heat exchanger. That was one of the last parts I printed, so I have it here. This is one of the heaviest ones we did so far. It's an inline heater system for our cleaning station, and this is they really did a great job in debinding and sintering this part. So really one of my favorite parts as well. So here you see to almost at the end of my presentation, this is the printer we're offering at the moment. It's our laboratory system, the Hammer Lab35. It has a building field of 90 × 56 millimeters and a resolution in the printing field of 35 microns. So this is the resolution of the imaging system, of the projector unit. Depending on the powder, we can print with a slight thickness from 10 to maybe 100 microns, but it's always dependent on the powder. If you say, yes, the building field, that's too small for application, don't worry. We come up with a production system with roughly 200 × 200 in the following years. So we will also update on that. But we think this system, the laboratory system, is a good way to start the material development, get used in the LMN manufacturing process, and then upscale. Material-wise, stainless steel is the material we work most with, or 17.4 another steel type. But we also have printed some applications in copper, tungsten, and titanium. And if you're interested in a certain material, please feel free to contact me afterwards, and we can discuss what's possible. To sum it up, what are the advantages of our LMM technology, of our metal printing technology. Compared to other additive manufacturing technologies for metal materials, we can print parts in the highest resolution possible, also with superior surface aesthetics to any other metal additive manufacturing technology. That's what you see afterwards in the presentations as well. That's just a big benefit of lithography. Because we have a sinter-based technology, we can process the widest range of materials, because our material only needs to be available material, and also because we use this feedstock system, the material doesn't need to be flowable, so we can work with edgy powders, and this is also benefit if you compare it to other powder-based technologies. The printing process, it's relatively simple. As you've seen in the machine, you can really change material quickly, put in a new machine really fast. You need to consider the binding and sintering. This is a crucial step. So, but here we offer our expertise, and we have a strong network of experts in our connections as well. With that, this was just a brief introduction into our additive manufacturing approach. Please feel free to contact us after me or my colleagues in the rooms, in the chat rooms afterwards. And I thank you for your attention.
Gerald, thanks for that. You've certainly got the attention of the audience. There's plenty of questions coming in, so I hope you've got a few minutes just to answer a couple of those with the audience here. So what I'm interested in, have you printed any precious metals?
Yeah, precious metals. We are just starting a few customer projects with gold, so that's going to be really interesting. But if you really, but in our experience, if the powder morphology is similar to what we are used to, so for stainless steel we're using +5 -20 microns, so this powder range, which is similar in metal injection molding. The D50 is around 12 microns, and if we can get our hands on a similar powder, maybe in gold, platinum, maybe silver, then we're fairly confident that we can achieve similar printing results as well. So the printing is not really the biggest challenge here. It's really the debinding and sintering, the post-processing.
And so what's the advantage then of LMM technology, say, compared to binder jetting or other AM processes?
Yeah, the big advantage for us is, as I tried to mention before, is the lithography-based approach. Because with the projector unit, if you polymerize it from above with the 35 micron resolution, you see this afterwards, not only in the complexity of parts you can produce, but also in the surface roughness of the final part. So here, of course, the surface roughness of the final part also depends on the particle size of the powder you use. But together with the lithography-based approach and the really fine particle size, we can achieve surface roughnesses below 5 micrometer Ra in every printing direction. And this is the really unique thing about lithography.
Okay. Some more questions coming in. Make sure you do use the Q&A section for your questions. We'll try to hit a few of these now. So most popular question is, how accurate can shrinkage be calculated? There's some concern there that you're dealing with very small parts. Is this going to be accurate enough?
Yeah, the binding and sintering, as I mentioned before, that's the challenging topic. But for us, since we have this feedstock system, we have also the advantage of a powder-based system that the powders is more held in place by basically by a photopolymer or by the liquid system we are using. So we have a quite homogeneous shrinkage in X and Y and Z. Okay.
Another quick one. Can you recycle the feedstock?
The feedstock we can recycle. It's basically when you do this decaking process, you catch it in a basin or in a small container. You can directly pour it back into the printer, or you make a block of feedstock and put it back into the printer as well. So yeah, this is the material you can recycle quite easily.
Okay, another one on the specs here. So what is the largest size you can print?
The largest parts we printed so far was this part I'm holding here. It has about 200 grams in green part. The green part weight And of course, I've shown it in the presentation before. You have some shrinkage during the binding and sintering, and yeah. So the largest part, the largest green part, to answer it in millimeters, was about 80 millimeters tall.
Okay, I am aware that we've got lots of questions there, and we will be able to have a time after the main presentations are finished to come back to those. So if we haven't answered anything, don't worry, there'll be an opportunity to put these questions directly to Incus during the networking. But also, I do want to make sure we do get to our other presenters as well. So, Gerald, thank you for your presentation. See you in the networking in a moment.
See you later. Thank you so much.
Our next company is Lithoz. So Lithoz is a world-leading provider for ceramic 3D printers and materials. Their innovative LCM technology, along with their wide range of durable, thermally resistant, and even bioresorbable ceramics, enables rapid production of parts for a diverse number of industries. And to tell us about that, we have David Schuller, who's a business developer at Lithoz. And David, you're going to be giving us some insights into the manufacturing areas in which 3D printing is the better choice compared to other production technologies. So, David, the virtual floor is yours. Please take it away.
Perfect. Thank you so much, Michael. I hope you can see my full screen. I assume so. And it is my pleasure today to talk about company Lithoz. We mainly focus, not mainly, only focus on ceramic manufacturing. And my name is David. I'm responsible for business development here at Lithoz. And the goal is to put our technology and put it more into the industrial field because we are already very active in R&D. Lots of our customers use it in serial production, and they want to push it further in this direction. So I talk a little bit about the company and then jump right into the topic. So what is Lithoz? What are we doing? We are developing and manufacturing the 3D printers so you can print your ceramic parts. There's always an important triangle, I like to call it. So it's the machine itself, it's the software, and it's the material. So you need those three components in order to create a part that will be of high quality in the end. If one of those parts doesn't work, if the material is not perfect, you will not get a good result. So that's the expertise we bring in there. We're about 80 employees, so you have an idea, and we have 2 locations, one in Vienna, the other in the United States. And there's one figure I would like to draw your attention to, which is the almost 100 machines that we put worldwide already. And 25% of those of our customers, they have 2 or more machines. So why am I telling you this? This is simply because once you really get into the topic and then you get into the niche, you understand the specific needs and your demand will increase. So I would like to talk about those 4 questions. Why are we doing it? How are we doing it? What are materials used? And what are the applications? So why are we doing it? Or better said, why are our customers?
Hi, David, I lost your audio briefly. But...
Excuse me?
Oh, your audio is back. It's okay.
Okay. So one of the most important things is the freedom of design. So you simply can create pieces with additive manufacturing that could not be done before. I like to use the term that with additive manufacturing, you can drill around the corner. And this, I think, gives a good insight of the future potential. You can integrate functionalities into existing pieces, for instance. A second very important reason to go with additive manufacturing is the prototyping and the time to the market. So earlier or still today, prototyping is a costly and also time-wise a very hard process. And with additive manufacturing, you can do it just by printing it. The perfect example you see on the screen, you have 5 different wheels here, and each wheel has a different number of blades. So by printing different types at the same time, you can find out which is the best design. Recently, I've also heard more often the digital production. So what will your production look like in the future? If you look 5-10 years ahead, digital production is becoming more and more important. and additive manufacturing could be one important tool inside the digital production. This reason I've mentioned before already a little bit, it's that with the freedom of design and the prototyping, your customers or you as yourself, you can change your existing products for new markets, or you can create completely new markets. Remember the number I showed you, 25% of our customers have 2 or even more machines, and that's the reason. And finally, the customization of products. So this is a big topic in the medical world, because here talking about implants, each and every implant is a customized piece. Good, so that's the why our customers are going there. Now I would like to talk about how is it done. This is fairly similar to what Gerald has explained. So we have a process starting with a cut design. You can use any cut software you would like to have. And this is then introduced into our 3D printer. So our software slices it into hundreds of layers, and it is printed. What we receive is a green part that requires post-processing, so the sintering, in order to get the final density of the product, which of course, we want to have. What does it look like in more detail? On the right side, you see a schematic. So you have the number 2, where we have a transparent vat. We pour the slurry, that's our material, is called slurry. We pour it there and dip with the number 1, that's the building platform, into the slurry. And from the bottom, we have the blue light that structures each and every layer in a 2-dimensional way. And doing this hundreds of times will create the desired 3D part. So I have a short video which illustrates this. You see the material in the vat, the platform dips into the material, then comes blue light. So the layer is structured and hardened. And that's the whole process, which is repeated over and over again. So once more, blue light means hardening. And yeah, this is the principle of the technology. Good. So I go on with materials. Ceramic is not only ceramic. There's a lot of different ceramics that can be used. And you see here a variety of things that we have worked with already. I want to draw your attention to 3 parts. Number 1 is the regolith on the left side. I want to name this because that's a nice story. The space agency approached us and they wanted to print regolith because or I'm telling you that regolith has very similar characteristics like the moon dust. So if once in the future we live on the moon, we can print stuff up there. In the middle, the blue part is hydroxyapatite, and next to it tricalcium phosphate, which is very important for the medical world. And on the right side, you see alumina and zirconia, which are our working materials for the industry and dental field. Important here is to know if you have a specific powder, we make it printable. So we have a couple of material scientists here in Vienna, as we are also a spin-off of the Technical University. We develop materials and powders for you. One part that often comes up in the discussion with our clients is about the quality of the material, really, compared to conventional methods. So you see here our LCM, that's our technology, compared to isopressed samples. On the left side, the macroscopic observation shows no difference. And if you test it, we have done this externally, you also see that density, hardness, and the bending strength is the same. So this is really a technology that can be used for industrial production. So we don't have to shy away from any other conventional production methods. Good. Then I move on to the last part of the presentation, and also I have a small surprise in the end after the applications. So where is it used? I think one of the most important things here to understand is that we, as Lithoz, we're the experts in the printing process. Where it is used, all the applications will, of course, also depend on you, on the market, to tell us where do you have a need, how can we go there? Can we maybe change a part that is now made of metal to ceramic because of the higher abrasion of ceramics? So this is a collaborative approach that we have. But still, I want to give you some insights. So we are heavily working in the industry field, in the medical field, you see on the right side, and also in the aerospace sector. The right bottom part is a casting core used for complex cooling channels in the turbine production. So some more ideas about the application in the dental industry. You can imagine today, if a patient, for instance, is gnashing his teeth, usually while sleeping, there's an important layer of the teeth disappears. And the dentists today, they use a minimal invasive approach, which means they don't want to rip out the whole tooth just because you lost a small layer. And very thin top veneers is a very good solution for this. And by coincidence, 3D printing can do this in a very good way. So traditional production methods reach its limits here. And with additive manufacturing, we print with 25 microns on top of each other. So this is a very good application. Also, not only for the printing, this is a completely digital production process. So at the dentist, your tooth or your mouth will be scanned, and this will be then delivered to the company who's doing the printing. Maybe you remember in the beginning, I told you one reason to go for additive is a digital workflow, digital production. Here you have one example out of it. Another example from the medical world is the bone healing process. So sometimes patients have a very critically sized bone defect because of an accident, maybe because a tumor had to be removed. And it means that the patients cannot grow back the bone themselves. So how it is done today, if you have a bone defect, a bone from your own body is taken from another space, like for instance from the hip, and is then used for the implant in the shoulder, for instance. And of course, this is a lengthy process. The patient has to undergo at least 2 surgeries. This costs a lot of money. For the patient, it's not very nice. And with additive manufacturing, we print the implant with our technology. And one thing that still amazes me is that the ceramic has a bioresorbable effect, which means that it dissolves over time, and the real bone has the potential to grow back. So this is quite amazing. 2 more examples I want to give you. One of the chemical industry. So the purification process, when the production of vaccines or pharmaceuticals, we know is a very lengthy process. Especially today, we know that it's important that it goes fast. So if you want to have a vaccine or another pharmaceutical process, the purification is important. This is done via state-of-the-art technology, so chromatography. But the filters that are used in the chromatography, they have certain drawbacks. And you see this filter here, they have very small channels. They are around 100 micrometers, and they also have different shapes. So there's a rectangular shape, there's a round shape, there's a triangle. And by this, we can increase the purification process. So if you want to say it so, that additive manufacturing can help to improve the healthcare overall. The last part I want to show you is about mass production industry. I already told you about this. So in the early days, we were working with R&D, and a lot of our customers started with R&D, and today they are producing in series. You can see with one machine, you have the possibility to produce more than 200,000 implants. So yeah, the question is, how far will you go with it? And I hope I could give you a nice insight into the company, why we do it, how we do it, which materials we use, and yeah, the latest part that we are already in the industry and we want to go even further there. I promised you there's one more thing. So check out our YouTube page, because we have lots of videos to the left. We call it Lithoz Explains. We have a couple of short videos that explain really step by step why we do things and how we do them, and also how far will you go. On the right, you see some nice videos about serial production. And now the surprise, ta-da! We have also a multi-material printer, which has the ability to print 2 different materials. So it's ceramic, or ceramic metal, ceramic plastic. Yeah, this we can discuss in the after session, or you contact us directly. Thank you so much.
A lot. Thank you, David. There's a lot of information there to take in for sure. And, you know, ceramics, I think, is one of those areas which isn't really as widely understood or polymers or metals. So how would you, you know, if you were looking to get into ceramics and you don't have any existing knowledge, how would you go about that?
Yeah, and we actually have a quite good example here in Germany. We work with a couple of service suppliers, ceramic service suppliers, that also work with different technologies and with our 3D printing technology. There's a company called Steinbach. They had no ceramic knowledge before, and together with us, they built up this knowledge. So you remember we have a university background, so to say. So that's the best example that you don't need a lot of ceramic know-how to start there. Of course, it's favorable, but it's also possible without. And most important point here, we follow a collaborative approach.
I noticed something in the chat that's just popped up about an event which I'm sure a lot of people are excited about next week, which is the AMUG event in Florida. And I see that all three companies will be attending. So that's a great opportunity if you are heading to Orlando to learn more. If you can't wait until a bit later,
you can ask my colleagues if I missed something here in the presentation.
You mentioned production there. Maybe can we get a prediction out of you? When do you think serial production of additive made parts is realistic?
So the answer is simple. The time is now. So we are already in serial production. And if you watch the first video of Lithoz Explains, we will have a nice graph there that shows that really in the next 2 years, I don't have all the numbers in my head now, the next 2 years, the market is expected to double. And if you look forward 5-10 years, you know, when the market starts really to understand the advantages of additive manufacturing and ceramics, it will even, I think it will be a factor 10 if I'm not mistaken, that it goes up. There are certain predictions about this. So yeah, I'm looking forward to this.
Speaking of not having the numbers, here's one which maybe you can answer, maybe you can't. But the most popular question in the Q&A is, how much is a liter of Al2O3?
1 liter.
Yes.
So I mean, this is something I like to discuss in the separate rooms. So there's no how to say.
Let's save that one for a bit later then.
No, but to put it simply, to give you an answer here. So our material, of course, is a little bit more expensive than any standard ceramic material you will find, but you need to take into consideration the whole production process to look at a certain productivity. I think that should be the answer. Understood.
So I think that was an anonymous question, but if you asked that question and you'd like to know more, do track down David afterwards. I'm sure he can give you a more detailed rundown depending on your needs. Okay, here's another question. What size particles are needed if you want a slurry made of a new material?
The size particles, so I'm not the material developer, so I don't have the number in my head, but we offer this material development, and then all the details will be fetched there. So whatever kind of material you have, we need maybe 1 or 2 liters to make a full material development, or better said, first a feasibility study to see if it works. Secondly, printing certain geometries like a simple cylinder, and in the third step, printing whatever you would like to have, and all the details need to be checked with our material scientists, because this is a really
another question about materials. How important, regarding the feedstock, how important is the shape of the particle size distribution?
Good question. I'm sorry, shape of the particle sizes is beyond my reach. Maybe in the after session, my colleagues can help me out there, because I know that
they're really sticking it to you today, aren't they? These are the real technical ones. So don't worry, they're going to be.
That's perfect. And I'm just here to present how it works. And like I said, we have next door, I think, 10 material scientists, that's their daily business.
They're going to people want to know all about this. So
exactly, yeah.
What we're going to do is, because I want to give everybody a chance to present, David, I'd like to thank you for your time. If your question hasn't been answered, don't worry. There will be representatives from Lithoz around in the networking office, so do hang around for that, and we can get you answers to all of your questions to a level of detail that you'll be satisfied with. So David, thank you again, and see you at the networking in a moment.
Thank you. See you later.
Okay, so our final presentation this afternoon before we move to that networking is going to be from Cubicure, who are a system provider for innovative photopolymer materials and industrial 3D printing hardware. And their technology portfolio is based on the revolutionary hot lithography process, which allows the printing of high performance polymers. So really covering all the bases today. Robert, you're joining us, and you're the CEO and CTO, and also one of the founding members of the company. So with no further ado, please take the virtual floor and tell us all about Cubicure, please.
Yeah, thank you, Michael. Hello, everybody. I hope you can hear me. Hello to Cubicure. I will talk about polymers 3D printing today, also lithography-based, a process we call hot lithography, and what it's all about, I tell you in the next minutes. So first of all, we are another Austrian company, so we are located in Vienna, the same as Lithoz and Incus. We have around 40 employees at the moment. We have a strong R&D section, and we are dealing with polymer, photopolymer materials, as well as the 3D printing systems to process them. In our portfolio, as you can imagine, you find the photopolymers. So we are actively selling resins. We are developing resins by ourselves, but also together with partners or for partners. And we are developing and selling 3D printing systems with a strong industrial focus. So we're strongly B2B focused, and here towards the industrial use of 3D printing systems. Beside that, all of us, we need solutions for the digital workflow. So here we have a software product we call Cubicure Support and Slice. If you're interested in this, please ask us later. And of course, we are offering service and training for you to use these 3D printing systems in your manufacturing. In Cubicure, we have a strong focus on the combination of process and material. And at the base of that, it's really the material. If we do not have the right materials for an industrial applications, we will never see it in an industrial manufacturing process. We will never see it scale. So first of all, the material needs to fulfill the requirements of the application. And then, of course, it's about productivity, and it's about the process quality itself for industrial use. In our case, we are using very selectively heat and light to bring special polymers into shape. And how we do that, I will show you in the next slides. First of all, going a little bit into detail about the hot lithography, it's very important to understand that the classical photolithography processes are very limited in their process window. So we have here a diagram which shows the viscosity of a photoresin over the temperature where you use it in the printer. And this small gray box you see here on the left side is a typical process window of a standard SLA or DLP machine. But it would be way more interesting to use other chemicals, which to process them, you need a way bigger process window. We indicated it here with a big blue process window, and that's exactly the process window we opened up with the hot lithography process. And to do so, you will see that later on pictures and videos, we always use some kind of coating process to bring our viscous materials to provide them to a process zone. And we also use heat to limit the viscosity to a reasonable number. As you can see here, we use up to 120 degrees C in temperature. And at this temperature, we can process resins up to a viscosity of 20 Pascal seconds. To give you an idea, 20 Pascal seconds of viscosity, that's somewhere between honey and toothpaste. So it's already quite viscous, but our machines are able to process these viscous materials and slurries. And that's important because now with that high viscous resins, we can really generate performance polymers, which you would use for your applications. Here you see a short schematic how this is done in a Caligma machine. So this can be done in different ways, but this is how it's done in a Caligma machine. So you have a material wet, which is indicated here in the glass plane. In our case, the light information comes from below. You see it on the left side. In our case, most often it's a laser scanning system. And so we provide a thin layer of photoresin, and then it gets exposed with the layer by layer information. I hope that video is running smoothly, at least that you can see what is going on. So in this vat, so we do not have a full vat of material, but we always provide this thin layer of resin. And in this thin layer of resin now, on the light information is put into, and then with very fine detail we can write objects and build them in the third dimension. And the good thing is this is working for soft materials the same way it works for hard materials. So the process window is really quite broad, also in terms of the final material properties we can process here. Our first system, we introduced that in 2017, is our Caligma 200 machine. So this machine is supporting this hot lithography process window I just described, and it's working with a 4 or 5 nanometer laser with a very high resolution. So we're talking about 20 microns in the laser spot, and of course you can choose now in the layer thickness roughly between 10 and 100 microns, and this allows you to print fantastic structures with very fine details over a quite large building platform. So 200 times 100 millimeters, still small for industrial scale, but quite big when it comes to this tremendous resolution. If you're interested in the details of the process, please maybe after this session, take a look in our YouTube channel. There we have a nice CGI video where you see the process working in detail. Let's talk about materials now, because I said this is the most thing. This is a very prominent development at this point. So we do that together with Evonik, in this case for elastomers. These are polyester-based elastomers. The nice thing is, for the first time, these are real elastomers coming to the 3D printing world, coming to the lithography world, indicating here a very low glass transition temperature. So that means it's still elastic at minus degrees C. So that's important for the daily use. Think about sportswear, think about shoes maybe, or think about also applications in automotive environment. So you need a broad temperature window to use these elastomers, and we can support that with the Invinam brand we're doing together with Evonik. Yeah, here you see another example printed out with that material. So what we want to show here is that you can also do very delicate structures, which is also important, because typically when you injection mold rubbers or elastomers, it becomes very difficult to do thin-walled objects. But with 3D printing now, a lot more is possible, and really crazy geometries are possible out of these elastomeric materials. Very important note here, for elastomers, you need high load cycles. So the Rosflex test is a very famous test here, and this has already been done together with Evonik. We see more than 500,000 load cycles here for the materials, even at minus degrees temperatures. So we really have a very nice elastomeric material, which is ready to be 3D printed in our Caligma machines. Yeah, besides that, we have Cubicure own developments. So our multi-purpose material we call Evolution. It's on the market also since 2017. It's in very broad use for functional prototyping, for small series, and for all kind of parts. Think like similar to polypropylene parts, where you need a functional part and which can be printed quite easily and quite fast. The same is true for precision, which is really on the edge in terms of the precision and accuracy you can realize with the printing system. So we see applications like sensor housings or even cleaning nozzles, very delicate small parts, which are already also in series production at our customers. So very interesting material class also for the future are flame retardant materials. So in the whole AM field, we see tremendous interest coming from the electronic industry. And this industry, of course, needs flame retardant polymers. They need heat-resistant polymers, so they have very high demands for the materials, and we are able to provide first solutions for that. So first of all, I want to introduce the Evolution FR for flame retardant, which we introduced to the market in 2019, and at that time it was the first resin, photopolymer resin, which fulfills UL94 V0 requirements. You see the values later on. And I also want to introduce to you Thermoblast, which is really our best performing material when it comes to these special applications. So you will see it's very heat resistant, and it has tremendously good flammability characteristics, flame retardant characteristics. So first of all, let's shortly talk about the Evolution FR. Again, you can compare it to some kinds of polypropylene. You can use it roughly up to 80 degrees C, and as I said, it was the first material to pass this UL94 V0 test, which is a famous flammability test in the electronic and mobility industry, which is very important for these kinds of materials. We talk a lot with electronic companies, with connector making companies and mechatronic companies. So we already prepared quite some data. If you're interested in that field, as you can see here, we have data for glow wire flammability, glow wire ignition tests. We already look deeply into things like dielectric strengths, electric resistance, and all that stuff, which is really needed when you want to bring these materials and these processes to industrial production. Coming back to the Thermoblast material, which is superior in at least two aspects. The first one and the most important one is the high heat resistance. So you can use the material up to 300, roughly 40 degrees C. And for such class of material, it has still interesting toughness and elongation at break. So it's not brittle as glass. Of course, it's a stiff and strong material, which is rather brittle, but it's not as brittle as glass. And it's really a good material for like connector parts and all that stuff. And as you see indicated in the pictures, you can do things which are not possible, of course, in classical injection molding. And the second most important value is the flame retardancy. Really, this goes down to very thin walls. So this is completely new to the AM industry. This is even benchmark for traditional polymer industry. So 0.4 millimeters wall thicknesses, which are still flame retardant. This is really a benchmark value in the whole polymer industry. Of course, you can print all these materials with very high resolution. In this case, down to 50 micron layers, which is very good for these fine connector parts. I also have a short video for you showing these flammability tests. So this is the UL94 V0 test, which basically comes down to that the materials need to extinguish the fire by itself. in a short period of time. And these classes of materials can already do that. Yeah, so I think I'm running out of time, so I hurry up a little bit. So what is hot lithography used for so far? Customers already use it for spare part production, for example. In this image, you see always the injection molded part and then the spare part, which is 3D printed by our hot lithography approach. And to do that, some of our customers already heavily use computer tomography, for example, to replicate the original part to be able to digitalize that part and then to reproduce it in a 3D printing process. And these customers, of course, they also use the computer tomography to deeply look into the details of every part and look into the manufacturing quality. And it really comes through to the detailed accuracy, to the reproducibility of all these parts, and all that is needed when it now comes to serious production. And I'm very proud that Cubicure has really done a good job here in the last years, and our machines are very reproducible and bring good quality in their printing runs. Okay, looking a little bit into the future, of course, we are talking about industrialization, and industrialization also means throughput and productivity of the systems. This is our real approach here in Cubicure. So first, we need to have the materials. So this is done now for very interesting sectors. We have the materials now, and now we need the next step in productivity. And this is what I show you here. On the top side, you see the Gmeiner process. This is already used for small and even middle series production, when the parts are smaller, of course. Individual part production, spare part production, as I said. Of course, it's used for R&D purposes. It's used for part development. But now the next step is bringing the materials and this production quality on a big scale to the industrial floor. And this is what we are already doing. And on the lowest section of the slide, I give you a glimpse of what is happening here. So we already have high throughput processes on hand. We are already running them. Some of our customers are already running them in specific industrial fields. And I think we will see these systems also very soon on the market. And here, between the Gmeiner and the next system class, so to say, we see a throughput increase of a factor between factor 20 to factor 100. So we're really talking about industrialization now of these hot lithography processes. I give you two more examples of this productivity, and I think then I consumed my time. So the first thing is, as you can see here, a full printing platform, a 1 meter long printing platform with small electronic parts. You see the parts on the right side. So these are very small connectors. I think they're 16 pin connectors, and you can print like 2,000 of them in a short period of time in only 2 hours. So that means with a single production unit, we are already entering the tens and 20,000 parts per day regime, which ends up in million and even for small parts, a double-digit million parts area with single production units. So we are really entering the mass production field with AM technologies, something which was unthinkable a few years ago, but this is really happening now. And the second example that shall always remind you that in additive manufacturing we always also talk about part volume. So if the parts become bigger, then obviously the throughput, the number of the parts go down. So that's inherent for additive manufacturing. But of course, with these large systems, you can already you can also print a reasonable number of large parts in a very short period of time. So for that example, we have a test tube holder where test tubes of biomedical industry are placed, for example, for an auto sampling process. And here we see a full tray printed in 8 hours with these test tube holders. You see here, these holders are good to use, like over 500 of these test tubes. So we're really talking about numbers. And you have a full production flexibility because you're digital. So basically, you can modify, especially in this biomedical industry, very interesting, you can modify the parts for every single printing run. So you have full production flexibility, which I think will totally revolutionize the polymer printing or polymer manufacturing industry in general. Yeah, and with that, I want to say thank you. And our team and myself, we are there for questions right after the talk now, and of course also in the future. Thank you.
Excellent presentation, Robert. So much information there, and great to hear the optimism about industrializing AM as well. So quickly, let's take a few questions from the audience, and one which people really want to know about is to do with viscosity. And the question here is the 20 pascals second at room temperatures, or is it when it's hot?
It's also when it's hot. So the 20 pascal seconds, that's really only the viscosity. You can use the 20 pascal seconds at room temperature. You can use it at 120 degrees C. It doesn't matter. So you have really this full area of process window for your material. You can put your point anywhere here.
Okay, a question on material options. Are you able to print polymer equivalent to Teflon for thermal and chemical characteristics?
To chemical characteristics, no, at this point. So we do not process fluorinated polymers at this point. But of course, but we already do like polyamides, but not fluorinated polymers, no.
Okay. And what about the feature size limitations, and do they depend on the viscosity of the uncured polymer?
In the printing process, we are only limited to the optical resolutions of our light exposing unit. That's in most cases, these are lasers. So we're talking about like around 20 microns in feature size, around that number. When it comes to cleaning, it could be a little bit more tricky because you can print very delicate structures which you might not be able to clean then afterwards. But then we're talking like in microfluidics, there are some limitations when it comes to channel width of 100 microns and below. That's then really becoming difficult. But above that, we have also a lot of experience. Yeah.
And one final question on the tech specs, which is what is elongation at yield, not break? And that's referring to functional elastic versus non-functional plastic deformation profile. What does that look like?
Yeah, so typically we shoot for a range of 3 to 5%. Obviously, we do not reach that with every material, but it's possible to reach the 3 to 4% elongation at yield. Yeah.
Okay, I think I'll draw a line under the questions for now because we do want to get to the next parts of the event. Before that, I'd just like to thank Gerald, or Gerald rather, I'm pronouncing of the English version, which I know is not right, David, and of course yourself, Robert, for all the information you've provided today. And also thank you for everyone who's joined. It's really a truly international event. I've seen all sorts of countries popping up there. So we're going to continue the conversation now in a slightly different forum. We're staying on this particular platform. We're going to move to the networking session. So if you've not used Remo before, the networking session can be used either with your camera and microphone on, or if you prefer, you can stay on text chat there. You can double click to move between the different spaces on the conference floor. Representatives of each company will be available at the designated booths, and there'll be conversations taking place across the floor, I'm sure. And we'll have that open for the next hour. If you did miss anything today, there will be a recording, and there also we will be able to follow up with any questions that have been asked. But I'm just on behalf of the organisers today, I'd just like to thank everybody for attending and for fantastic questions. I know it's not a substitute to attend a virtual event, and hopefully we can get back to meeting in real events quite soon. And on that note, thank you all for attending, and see you at the networking. Good afternoon.